I'm a postdoctoral researcher at Chalmers University of Technology, where I study the stellar winds and outflows of these massive stars in our galaxy. So today I'm going to talk to you in kind of three sections during my talk. I'm first going to go through an overview of the evolution and stellar lifetimes of these massive stars and how these might differ to low mass stars. I'll then talk to you a little bit about radio astronomy, because what I do in my research is I use radio observations of these massive stars to kind of constrain the properties and understand more about what's going on in their circumstellar environments. And then I'll finish off by telling you a little bit about specific bits of research that I've been up to and some of the questions that are still present in the astrophysics field. So I'll get started.
I have a question to start off with.
Yeah, sure.
In what way are we going to ask the questions, if we have any?
I believe that there's a chat. So I guess.
Or could we raise our hands? There's this function where you can raise your hand. Is that fine?
So I, as a speaker, can only see my slides, unfortunately. But I'm happy to pause for a few seconds after any one of my slides. If anyone wants to jump in, feel free to just unmute yourself. Or if you have questions throughout, I'm happy for you to put them in the chat, or we can do questions at the end.
Okay, great.
Yeah, okay, great. Yeah, sorry about that. I can only see my slides from where I am. So the first topic that I'm going to go through with you guys is stellar evolution. And so we can consider the entire stellar lifetimes of these stars to be somewhat dominated by this parameter of how much mass they have when they're born. And this really does impact them right from when they're born in the stellar nurseries to the final endpoints of these stars, be it as neutron stars or black holes. So as I said, these stars, their lifetimes and their evolution is characterized by their stars. And we can kind of split stars into two different classes, either low mass stars. So these are stars which have masses of less than 8 solar masses when they're born, or high mass stars, which have masses of greater than 8 solar masses when they are born. And so our sun, for example, is a low mass star. And so it will follow quite a different path in its life to the high mass or massive stars that I actually study. And this mass parameter, or how much mass these stars are born with, influence a lot of the other characteristics that stars have. So this includes the stellar luminosity, or how bright stars are and how hot they get, the overall lifetime and how long these stars live for, but also the characteristics of the different stellar phases and how it experiences these over its lifetime. So you can see a little bit in the picture that I have here, the kind of different lifetimes that stars can experience because of their mass. So if we start right from when stars are born in these stellar nurseries, as we have a picture here, and these are these giant clouds of gas and dust, also known as giant molecular clouds. And so one thing to be aware of is when we talk about gas and dust in astrophysics, they have different meanings to when we're talking about gas and dust here on Earth. So gas itself isn't just a state of matter that you might come across in your physics lessons, but it's actually all sorts of hydrogen gas, so just hydrogen, or small molecules, so things like CO, carbon monoxide, carbon dioxide, just small molecules and atoms in space. And dust is a little bit similar to the dust you might find around your households. Dust is actually anything where you have collections of these molecules that have banded together or frozen out into these micron-sized structures, so a similar size to a hair's width. And so what you get is you have these giant clouds of gas and dust, and they collapse under gravity and become so dense that eventually the hydrogen gas that is present is able to undergo the process of nuclear fusion. And so as this nuclear fusion process occurs, then you get the release of heat and light. And it's with this process that as these collapse down, they form these spherical structures where the fusion is undergoing, and then you have a star being born. So then the main steady state process of a star's lifetime, such as the state that our sun is in, is this process of hydrogen fusing in the core of a star to helium. And this is one of the first points at which you can see how clearly mass has an impact on the life of a star. So the amount of time that a star spends on this main sequence, as we call it, fusing the hydrogen to helium, is very dependent on mass. A star that is a G-type star or of one solar mass like our sun is going to live on the main sequence for about 10 billion years, whereas a star that is only 10 times as more massive is going to have a much shorter lifetime on that main sequence for only about 30 million years. And additionally, although the initial mass of the star is important, these massive stars also lose a lot of mass through their stellar winds as well, even during this main sequence part of their lifetime. In fact, losing as much mass as the mass of the Earth every 3 years. So one of the things as stellar astrophysicists that we like to do is to create a good plot or a graph. And so here I've put in what's known as one of the quintessential graphs that we consider when we're thinking about populations of stars. And this is the Hertzsprung-Russell diagram, where we plot how bright a star is, or its luminosity, against its temperature. But when we're considering the temperature of a star, we can also consider the colour of the star as well. And so the hotter a star is, we can actually consider it to be a bluer star, and the cooler, it's more of a red star. And this is simply done because when we take what's known as a black body approximation of the star, and we consider the kind of peak temperature where its strongest emission is coming from, and match this to the wavelength that we're looking at of the light, we can then match this to a type of colour. And so this is how we can convert our surface temperature to this effective temperature from this black body radiation, and consider the different colours of stars that we're looking at. So stars themselves, as you can see, when they're in that steady state, they're on this main sequence. And this diagram kind of shows you what happens with all these stars on this main sequence. They lie in this nice central band across this image. And the only difference that causes these stars to lie at different points upon this main sequence is their mass. But then the mass also affects where they then turn off this main sequence. And so this will then affect all of the stages that stars go through when they are an evolved star. And this is when they're no longer just converting hydrogen to helium, but they're starting to fuse heavier elements, and they're starting to become less and less stable as they start to reach the end points of their stellar lifetimes. And so this is for massive stars where these supergiant phases begin. And so for myself, my research involves looking at these supergiants, such as red and yellow supergiants out there. So a little bit more. Yes, sure. Go for it.
How does the stars lose their own mass? How does it come?
So it actually varies depending on the types of stars that you're looking at. So for these main sequence stars that I'm talking about here, which have this hydrogen to helium fusion going on, you have, for a low mass star like our sun, it has various hotspots over its surface and various convective forces going on within the stellar interior that cause mass to be pushed out. And this is related to the magnetic field of a star like our sun, a low mass star. Whereas for these more massive main sequence stars, so the ones that are in the bluer corner, but they haven't yet finished fusing all their hydrogen to helium, what happens is the radiation pressure from them being these hotter stars and them fusing that hydrogen to helium, that's actually enough to then push the gas from their outer layers outwards. And this is what's known as a radiation pressure driven wind. But this is different to cooler stars, like our evolved stars, so these supergiants and hypergiants. They have stellar winds where it's less clear, and actually what happens is you get pulsations outwards from the stellar interior, and this actually pushes more dust out rather than necessarily gas. And so what happens then, this dust experiences pushing out even more due to this radiation pressure. So the inner fusion processes are releasing all these photons, and then these photons effectively bang into this dust in the outer layers and push this dust further out, causing what's known as a dust-driven wind. But this is very much an approximation of the various ways in which these stellar winds can form. And additionally, the mass loss through stellar winds is only part of the picture, because you can get other processes such as interactions between binary stars, where you get captures of the outer layers of a star by its binary companion, or you can get non-spherical outflows, so concentrated outflows of material being pushed out of the stellar surface. So it's a very complex picture. Is that a good enough answer? Any other questions before I go on?
I just wonder really quick.
What's the
difference between in the picture before this one?
Yeah, sure.
In the HR diagram that there's supergiants and giants. Is that only like decided by their mass, or is it something else that makes them like different from each other?
Yeah, that's a really good question. So the supergiants are these kind of stars that come from these more massive, we call them O and B main sequence stars. So ones that are 10, 20, 30 times the mass of our sun, and they turn off and become supergiants. And you're right in that mass is one of the factors that differentiates supergiants and giants, because giants, like red giants, are the kinds of stars that come from later stages of what our sun will eventually be. But as well as the mass determining this, what happens is the actual processes going on in the stellar interior are also different at this point. And so this is caused because these have different initial masses, but actually we also see that they have different behaviors at these late stages. That isn't just that one's bigger than the other. So for example, for a red giant star, it's got convective forces transporting energy throughout its interior. And this includes what's known as dredge up processes, where chemicals or chemistry of molecules like carbon and oxygen from the stellar interior are being brought up to the surface through various process, what's known as helium flashes. So this is where helium is being fused in very, very fast events in the stellar interior. And the effect to which this happens, these dredge up processes of chemical mixing within the stellar interior being brought to the outside, is actually quite different to these supergiants, where they still have more radiative forces going on and they're less reliant on this energy transport through convection. So the big difference here is that these supergiants and giants have slightly different chemistries when we look at them. And also that this is all due to their stellar interior being different, but that in effect is because of their different masses. So even though one is bigger than the other, this is having all of these other secondary effects as well.
Okay, that was really interesting.
Okay, great. Are there any other questions? Nope. Okay, well, do feel free to unmute yourselves and just jump in when you do have a question come up. So to go over a bit more of an overview about these late stages for these massive stars, as I've already said, you've got these supergiants where they've got this more complex chemistry going on in the center, because we've had all the hydrogen fused to helium in the core already. And so what you end up with in both supergiants and actually the low mass giants analogues as well, is you end up with these multiple shell environments where you have heavier elements forming in the core, but also this is then surrounded by shells of less heavy elements. So you'll have carbon, nitrogen, oxygen forming via fusion in the cores of these later stage stars, but then they'll be surrounded by shells of helium and shells of hydrogen, which as the core keeps contracting and the envelope keeps expanding, may undergo further fusion events. So there's a very, very complex picture going on for these later stage stars when you compare them to those main sequence stars we were talking about earlier. And overall, this leads to a picture of when you look at these stars in the sky, because their envelope is so expanded, they look huge. They have these huge, large envelopes, to the point that when you consider some of the examples of these stars, like Betelgeuse, its radius, or its diameter, as you can see here, is over 1,000 times the size of our sun. And when we actually look at pictures that have been taken of Betelgeuse in these, so at millimeter wavelengths, you can see that its whole radio photosphere, as we call it, stretches out to beyond the orbit, an equivalent of the orbit of Jupiter or Saturn in our solar system. So these are really, really massive objects. And I mean, our sun is already pretty big, but these are even bigger. They also actually have quite cold temperatures, even though these are just really massive stars. So even though these are coming from these really massive stars, they're actually as cold as or colder than our sun, which is, you know, we would expect massive stars to be way hotter than our sun, but because they're reaching this point where they are spread out over so much area, they do actually cool down to a few thousand Kelvin. So for reference, our sun is about 6,000 Kelvin, and Kelvin's a temperature scale we use in astrophysics. But red supergiants themselves have a temperature of about 3,500 to 4,000 Kelvin. So actually a little bit cooler. And then as you get these multiple shell environments and the core contracting more and more in these massive stars, this is where it gets really exciting and things start speeding up as well. So if you have a star which fuses all the hydrogen in its core to helium in about 10 million years, actually at these later stage events, it's going to speed up a lot. And so you're getting all of this helium converting to carbon, nitrogen, oxygen in only 1,000 years or less. And in fact, by the time you're getting to forming new elements such as iron in the core, it's only going to happen in a flash, in less than a second, once you get to that very, very late stage. And once you have your fusion processes have reached the generation of iron in your core, you are no longer able to fuse any new elements through nuclear fusion. And so the radiation pressure that's coming from the core of your star can no longer counteract the gravitational forces of all the mass trying to go inwards, which leads to this violent collapse of this stellar core and a violent explosion outwards of the outer layers. And this is what leads to those supernovae, and then leads to these beautiful pictures that we get here of supernovae remnants that are left behind, all this material that then dissipates into the interstellar medium. And so this is one of the main differences between massive stars and low mass stars like our sun, is for our sun, it's never going to reach this point where it can generate iron in its core. And so it's never going to reach a point where it's going to be able to have this violent collapse and explosion event of a supernovae.
Is it only the super giants that become supernova, or is it the giants as well?
Yeah, so it's only the supergiants. So giants are the next stage for low mass stars like our sun. So you need a star that is at least 8 times as massive as our sun to then create a supergiant after it's finished fusing all its hydrogen. And then after it is a supergiant, it's able to fuse enough and get hot enough in the stellar core to generate this iron. And so it's hot enough to then reach the limit of nuclear fusion, which is where you need to get to for your star to then have to contract and then explode outwards. So yeah, it's only the massive stars that create supernovae. Okay, I will continue. So the final stellar stages, so you have this violent explosion outwards of these outer layers of the star, and we'll come back to that a bit more later on. But in fact, the mass that a star starts with also determines what its final stellar remnant is. So it can either end up as a neutron star or a black hole. And this is because of how small the core is at the end. And how much gravity there is to collapse the core down. So for stars that are around 10 times as massive as our sun to around 25 times as massive as our sun, and these are approximate values, when these stellar cores collapse under gravity with the outer layers exploding in that supernovae, you're left with a stellar remnant that's known as a neutron star. And this is because what's happening is this neutron star is undergoing a process where everything becomes so compressed that you get lots and lots of the constituent particles of neutrons. But as anyone knows, your constituent particles cannot be in the same energy states or the same locations. So there's actually a pressure there holding them apart in different energy states and in different locations in the star, although they're still able to create very, very dense objects. In fact, neutron stars are typically on the order of 10 kilometers across. So if you think about the overall surface of a neutron star, it's going to be about 1,200 kilometers squared. And I looked it up. This is actually only 3 times bigger than the size of Gothenburg. So these are very, very small objects, but they do contain a lot of mass. They typically contain twice as much mass as our sun. And for the more extreme objects, so these are stars which have masses to start off with of greater than 25 solar masses, they actually are able to undergo such a collapse that they form the region of space-time known as a black hole. So I actually have a picture here of a really, really massive black hole. This is the radio picture taken of photons from just around the event horizon of Messier 87. And this is actually a supermassive black hole at the center of a galaxy, which is 10 billion times the mass of our sun. But even for stars that are just stellar black holes, so these are coming from these stars which are 25 solar masses, they are still pretty extreme objects. They contain masses of 3 to the 10 solar masses within a space which has a radius of only 30 kilometers. And these are also very extreme conditions because all of the information, so all of the light, is trapped beneath this surface known as the event horizon, because light is trapped by the fact that they're in a gravitational potential well where it cannot escape the surface of what's left behind by that stellar core. So just a couple more general comments about the overall stellar evolution. But for both low mass and high mass stars, a lot of material gets emitted by these stars, and for both low and high mass stars, you're left behind by a small stellar remnant. So I didn't go into detail, but for low mass stars, you're left behind what's known as a white dwarf, which is just a small object made up of primarily carbon, nitrogen, and oxygen, which then fades away because it's no longer able to undergo nuclear fusion. So these 3 stellar remnants are left behind: the white dwarf, or a neutron star, or a black hole by a star. But you also have loads of material that's been thrown out into the surrounding. And so as this dissipates and becomes part of the general interstellar medium within your galaxies, they actually then are able to form these new giant molecular clouds that I was talking about earlier, with only a little difference. What's happened is you've had processing go on in the stellar interior. And so these new clouds are going to have more chemical enrichment because they'll have higher amounts of various chemicals, and so won't have as much just hydrogen, but they'll have what's known as metals, which is all the other types of elements in the universe besides hydrogen and helium. Astrophysicists like to simplify things. So what happens is then you have these new star-forming regions, and these can actually then lead to the creation of new stars, and stars are very, very good at recycling. But also what happens with these new stars is they're more likely to have planets around them. And so this is one of the things that has led to the creation of our solar system, is by looking at the various elements and chemicals in our solar system, we know there had to be a prior supernovae that went on in our solar neighborhood before the creation of our current solar system. But in general, you just have this continuing life cycle going on, whether you have the creation of a solar type star or a massive star. And it's also important to know that several stars can be born in what's known as a stellar cluster. So stellar clusters are located throughout our galaxy. It's where you have crowded regions of our galaxy where you have many, many stars in probably what can be considered a small space astronomically, and they're all quite crowded together, although on our terms it's still a very, very large region of space. And these are good environments to study, and I'll go back to this later, because these are regions where all the stars were born at around the same time in the same giant molecular clouds, so they have similar ages, they'll have been born in a similar environment, so they have the same metallicity, as we call it, so amount of chemical enrichment and different types of chemicals. So their main difference for why stars then look different in these same regions is purely down to their initial masses and the mass loss that they lose during their stellar lifetime. So just before I go on to the second part of my 3 parts of my lecture, does anyone have any more questions immediately straight away about the overview of stellar evolution?
I have a question. Is the black hole expanding, or how is it going with the black hole?
So with black holes, there's actually theories about this, that there's a process known as Hawking radiation. And I'm by no means an expert on black holes, unfortunately, but what happens is you can get these quantum tunneling events from the surface of a black hole where you do get things like neutrinos or small amounts of particles actually then dissipating outwards purely due to these like quantum events happening at the surface. So there is some thought that black holes will eventually get smaller over a very, very, very long time. In terms of expanding, you do also get capture events. So if you have accretion events of stars or other objects nearby that then fall into the event horizon, then it could get slightly bigger through accretion-fed processes. So you can kind of get both things, but on the whole, if you have a black hole there, the size of it is such that, and the density of it is such that you'll need to throw a lot of material into it or wait a really long time for any of this Hawking radiation for any significant changes in its size to occur.
Yes, thank you.
Yeah, okay. So, yeah.
About the these like layers in the stars with different types of elements? Because I'm a bit confused about if there's like when there's fusion with the hydrogen from the start,
Yes.
and then it goes outward from the core. Is it like that the hydrogen fusion goes outwards, and then when it's gone all the way out, that it starts with the next element? Or is it like when it goes one shell, then the core starts with the next stage?
Yeah, that's a really good question. So it's very much more like your second scenario there. So you have the stellar core itself, which is going to be within the whole stellar interior, and so you're not in a process where the entire stellar interior is going to have turned all into helium and then it's going to turn all into the next element. What happens is very much at the very center of the star, at the core of it, you have the hottest and densest area of the star, because it's right at the gravitational center. And so what's going to happen is you're going to have the most fusion events occurring within that core. And so that's going to be the first area where you're kind of converting all of the hydrogen to helium as possible. Whereas as you get further out from that stellar core, you are still going to have a slower level of this nuclear fusion ongoing. And this then leads to that shell structure that you then find where the core has converted most of its hydrogen to helium before the outer areas of the stellar interior have. And so this then leads to having a core which then is able to go to heavier elements much quicker than the shells around it. And so you end up with these kind of shell events of a helium core and then a hydrogen shell. Then you end up with things like a carbon core, a helium shell, and then a hydrogen shell on top of that. And it gets more and more like, I think the analogy used is like you have various different layers like an onion. So yeah.
Okay, cool, thank you.
Okay.
I have a wondering kind of. I read from an unreliable source, I should say. That,
okay.
Yeah, so it's just going to be maybe a yes or no question, I guess. Yeah, when you reach the event horizon, what it said was that the future light cone is pointing towards the black hole, which would also mean that trying to move back past outside of the event horizon, not towards the black hole, would mean that you're trying to move towards the past. Is this, is that the reliable information or not?
So I don't know, I'm not an expert, unfortunately, on the processes of special relativity and everything that goes into black holes. But I have heard before about this idea of having this future light cone. So there is something to it. Because as you are falling inwards to this event horizon, time is just becoming more and more and more stretched out. So it is possible that because things are happening quicker, the further away you are from a black hole, I mean, that could then be seen as time passing by more so, and then you have what's known as this future light cone. But I would definitely recommend looking up, stuff that Stephen Hawking and other popular science writers have written on the subject to get a better overview than what I can tell you.
Okay, thank you.
Okay. So yeah, I will continue on my second part, and then I'll pause again, and then I will finish the talk, and then I'm sure there'll be time for questions after that as well. So a little bit about why we study stars with radio astronomy. So before I get into it, stars themselves, you obviously might think that the best way to look at stars is with optical telescopes, because so many stars, the peak of their emission, or where they are strongest in emitting, is actually at optical or visible wavelengths. I mean, this is definitely the case for our sun. But actually, radio astronomy kind of took off in the 20th century, and it's quite useful for a lot of reasons. It allows us to observe areas that might be obscured by this dust that I was talking about, and it also allows us to look at areas just around the surface of the star. So when we talk about the surface of the star, the photosphere, we're actually considering what's known as the optical surface of the star, but by looking at these longer wavelengths, such as meters or centimeters, which is the wavelengths of radio data, we can then look at areas just around that or in the stellar winds or circumstellar environments. So radio astronomy itself, as I said, took off in the 20th century. The first sort of radio astronomy detections were made in 1932, almost accidentally, because radio was being seen as a useful tool for various other things like communications. And in fact, in 1932, Carl Jansky discovered emission from the Milky Way for the first time. But nowadays, this has kind of evolved even more from the little dipole telescopes of wires and stuff that people were studying radio astronomy with before. And we try to use multiple dishes. So some of my previous research, which I will briefly talk about later on in this talk, is using radio interferometry. And this is basically a process where you can use multiple radio dishes to get really, really good details of astronomical sources. For example, the well-known Hubble Space Telescope has an angular resolution. So this is the term we use for how fine a detail you can see of a source in the night sky, of about 1/20th of an arc second. But by using a radio array of loads and loads of telescopes combined together, we can actually get as good as or as fine a detail for these objects when we're looking at much longer wavelengths. And this is an important thing because I've put one equation on all my slides, and this is the only one, of the Rayleigh criterion, where the amount of detail represented here by theta rad, the angular resolution, is related to this relation between the wavelength of the emission you're looking at and the diameter of your telescope. So you might think that with longer wavelengths like radio and millimeter wavelengths, we're kind of stuck at not being able to just see as well as we can or as fine a detail as an optical. But by using radio interferometry, we can combine multiple dishes together where we can get rid of this diameter of an individual dish, and we can actually define our resolution by this d being the distance between the dishes we're using. And so this is what's known as a virtual synthesis aperture, because we're creating a new kind of massive dish out of all the individual dishes, as shown by the diagram I have on this slide. And this can be done because when we're looking for radio waves, we're not taking an image in the same way as we take an optical image. We're collecting lots of electrical signals. And so we can use some mathematical manipulation almost as a magic trick to combine and correlate the signals between all of our dishes together to then get these really good images out. So just a little bit of overview of some of my favorite radio telescopes that I have had the privilege of using in my research. This is one of them. This is the Australia Telescope Compact Array. And so this is in the southern hemisphere, so looks at the sources down there. And this has 6 22-meter dishes. But actually, we can get really, really good resolution with this because we can spread the dishes out so we can have a maximum distance between the dishes of 6 kilometers. And so this actually observes over a very wide range of frequencies. So we look at various different sources with it, from the millimeter, so having a wavelength of 3 millimeters, to 27 centimeters. Another type of radio array that you may have heard of is ALMA. This is based in the Atacama Desert in Chile. So a lot of the radio telescopes we like to use are based in deserts because we want nice dry skies. We can observe in radio during the day actually, which makes it a bit different to optical observations or visible observations with telescopes. But what we want is we want to avoid the presence of water vapor in the atmosphere because this can introduce noise into our observations. So a lot of radio telescopes are based very high up. So we're at high altitude and in nice cold desert areas. So the ALMA or Atacama Large Millimeter Radio Array contains loads of radio dishes. It's actually comprised of 66 dishes, 54 12-meter dishes, and 12 7-meter dishes. So although the radio dishes themselves have smaller sizes than that previous telescope array I mentioned, the ATCA one, which has dishes of sizes 22 meters, ALMA actually reaches even better resolution because it has so many dishes available that we can combine all the signals together from. And this also observes over a large range of wavelengths, from millimeter to sub-millimeter, so almost down to kind of infrared levels. But both of these telescopes are good for looking at areas where we want to kind of deal with things that could be obscured by dust, or perhaps look at various molecules and pieces of astrochemistry in space. And I also wanted to mention one of our more nearby telescopes that I have had the privilege of using. So some of you may be aware that Chalmers University of Technology here in Gothenburg has its own space observatory based about 40 kilometers away in Onsala. So this is the 20-meter single dish that I've had the privilege of using, because you can still get good information out even with your single dishes. You just won't have as fine a resolution as when you are combining all these radio dishes together. But this is also used in what's known as a VLBI array, so that's for very long baseline interferometry, where you combine loads of radio dishes from different countries even to kind of get really, really good pictures. So I'm aware that was a very brief overview of radio astronomy, but does anyone have any pressing questions from anything I've just mentioned?
I just wanted to recommend Kip Thorne to Trimmy when he talked about black holes. He's
Yes.
a really good physicist. Yeah.
Thank you.
Okay, great. I will just talk briefly for the last sort of 10 minutes of my talk about some of the research that I'm doing. So I'm studying winds and outflows of these massive stars using radio observations. So I talked a little bit to you all about the different stellar evolution cycles and lifetimes that these massive stars experience. And also they lose a lot of mass, all those different ways through the different stellar winds and outflows, as I mentioned earlier. But you might be wondering, okay, great, why do we care? Why study these winds and why study these outflows? So one of the major reasons that we have to study the winds and outflows and circumstellar environments of stars is because we can't study their stellar interiors. They have a surface. We can't look within the stars very easily. There's a little bit of work being done on some close by stars known as astroseismology, which is trying to get a bit of a picture, but for the vast majority of astrophysics history and even now, we're very much limited to looking at the outside of the stars. And so by studying the winds and the outflows, this not only allows us to look at how these winds and outflows are behaving, and also the mass that these stars are losing through them, but it also provides an indirect probe as to what's going on within the stars themselves, such as highlighting things like the chemical difference between the winds of these supergiants versus winds of red giants, which can help us understand that there have got to be different processes occurring in the stellar interior. So as I've said before, and I hope you're convinced by the end of my talk, mass is this really important parameter which really does define how a star behaves over its entire lifetime. And it actually then, the mass that it throws out impacts other astrophysical phenomena around it. So as I said earlier, these massive stars, they end up finishing their lives exploding as supernovae. But depending on the exact initial mass that a star has, it's going to have different stellar winds over its lifetime before its supernovae. And so it's going to have different material present in its environment already when that supernova explosion occurs. This is then going to affect things like the chemistry we see, or the destruction or formation of these dust grains that I've mentioned before. And it's also going to affect the light curve that we see, because there might be absorption or emission processes going on because you've got your supernova material running into this material that's already present there. And in fact, on an even wider scale, this material that's being thrown out into your galaxy, it's not going anywhere. We live in a conserved system, right? It's going to be staying there. Obviously, you have some material escaping a galaxy, but on the whole, from an individual star, the gas and the dust that you're throwing out is really going to define your galactic environment. And then it's going to feed into, as I've said before, these future star formation and star and planet system formation processes. So mass loss itself is a complex phenomena. So one of the things that impacts this is the type of stellar wind you have, or the processes that are going on with various episodic outflows, which is slightly different to just the general stellar winds. But also other factors as well. As I've said before, binarity comes into play. And this is actually important because we believe now that about 70% of massive stars exist in binaries. So if your binary companion, or perhaps even a triple companion, are close enough to your star, then they're going to interact with one another, and this is going to affect the material that your star is throwing out, or material being captured or stripped from your star by its companion. Some other things that come into play.
Do we know why most massive stars are in binary systems?
No, actually, we don't know why. So I think it must be related to the way that you have star formation processes going on. And in fact, as I mentioned earlier, we have these stellar clusters that we have within our galaxy. And it is believed that massive stars are more likely to form in stellar clusters, so in more crowded regions. So it might be related to that, where you have a preference in bigger giant molecular clouds for more massive stars to form and to form close together. So you have more extreme collapses going on nearby one another. But it is very much an open question in astrophysics to fully explain what's going on and why we are finding that so many massive stars are in binaries.
Thank you.
Okay. Yeah, and some of the other factors that come into play are things like rotation of a star and also its magnetic fields. And so this can be seen not only in just comparing individual stars to one another, but also in low mass stars to high mass stars, because it's been believed for a long time that low mass stars have more of a magnetic field, and so this is going to affect how these stars are losing their mass or their types of stellar winds that they have. So a little bit about how we observe stellar winds. So you can observe stellar winds either through what's known as photometry, so taking images of stars, and I will show you a couple pictures of that, but also through looking at the line profiles. So this is through spectroscopy. And so when you're looking at spectroscopy of a star, one of the big indicators that was first found to indicate that there must be a stellar wind is what's known as a P Cygni profile. So I have a bit of a diagram here, but effectively what happens is, because of Doppler effects in your wind, you're going to get a spread of your emission from a blue shift to a red shift, from a rest wavelength of a line transition for a molecule or an atom in your star. But in fact, because you have this dense stellar wind, what's going to happen is that your blue shifted part, so the part closest to you, is going to actually absorb some of the light preferentially. And so this leads to an absorption tail in your blue shift. And so you have most of your emission is centrally around the rest wavelength or in the redshifted region of the overall emission. But as well as this, we can also just detect general thermal emission from a wind, which then leads to what's known as just photometry or general images. And so this is related to bremsstrahlung, or braking radiation, where you have charged particles in your wind, such as electrons, that are passing by nearby atomic nucleuses or molecular nuclei. And what happens is the electron experiences a braking force due to the electromagnetic forces at play between the negatively charged electron and the positively charged nucleus. And this leads to the emission of photons. And so as you get further out in your wind, you've had more density, you've had more material that these wavelengths have been slowly reduced by, or the amount of braking radiation that has gone on. And so the wavelength of your emission is actually dependent on the density or the amount of material that you're looking at. So we can then say that when we're looking at longer wavelengths, we're actually probing outer regions of our stellar wind. And so this is a little bit related to what I talked about earlier. When we talk about the surface of a star, we can think of the optical photosphere, which is where your visible photons or peak of your emission is escaping. But then you can also consider what's known as a radio photosphere, which is actually within the stellar wind itself, but can be considered to be the surface of the star at longer wavelengths. And so a little bit of the work I've done previous to my time here in Sweden as a postdoctoral researcher at Chalmers. My PhD, or my doctoral studies, was based on looking at the overall stellar population of a massive stellar cluster in our galaxy known as Westland 1. And this is actually was detected back in the 60s, but hasn't really been systematically studied as much as other stellar clusters in our galaxy or in the Magellanic Clouds, because it has a really, really high level of extinction, which makes it a perfect candidate to study at radio wavelengths, where you don't have to worry about dust because you can kind of pierce through the veil, as it were. This is actually believed to potentially be the most massive young cluster in our galaxy, with a mass of 10 to the 5 solar masses. So it contains a lot of stars and a lot of material around those stars. And it's quite a young object as well. It's only about 5 million years old. So if you can compare that to the age of our solar system, which is about 5 billion years old, it's a lot younger. And it's fairly close by. In terms of galactic terms, it's about 15,000 light years away. And it contains this really, really rich co-evolved population. So as I said earlier, stellar clusters are good to study because you've got your stars in the same environment at similar ages. And it contains a rich population within it of 10 different red supergiants and yellow hypergiants. So those evolved lake type stars I talked about earlier, but also hundreds of these general main sequence O and B type stars as well. So kind of one of the highlight results that I was able to find by studying this is, so here I've got a general graph in the picture, and that's a contour graph of radio emission that we detected within this cluster. And here I've highlighted some of the individual objects we're looking at, which might look quite strange to you because you might expect stars to have a nice spherical shape, even at the radio photosphere, right? Like if we look at this thermal emission that I talked about earlier, even at the radio, you would expect a nice circular shape around your star. But what actually is happening is, because we've got these very, very dense, heavy outflows from these red supergiants and these yellow hypergiants, we've got these slow, dense winds pushing lots of material out in this cluster. What happens is we also have all of these O and B main sequence massive stars I was talking about earlier, and their stellar winds are a bit different to the stellar winds of super and hypergiants. They are also fairly dense, but a lot faster, and they also have a lot of ionizing radiation. So what happens is all of these winds from these hundreds of O and B massive stars in the cluster are able to push out throughout the cluster and actually cause this shaping intra-cluster wind. So we were able to consider where these different yellow hypergiants and red supergiants were present within our cluster, and we could see that there was kind of a directionality to how the winds were being sculpted, because they were being sculpted by these faster, stronger overall force of these other O and B massive stars that were then sculpting these slower, denser winds into these structures, pushing them outwards from the center of the cluster to the edges. So it really goes to show that we have a lot more to understand when considering how these stellar winds behave, because if we're looking at these crowded regions, we really are seeing that the stars are having an influence on each other when it comes to massive stars. And just a little bit more about why we might want to study red supergiants and yellow hypergiants. So as you could see before, they have these very large structures around them when you get them in these crowded cluster areas. And in fact, red supergiants and yellow hypergiants, because they have high levels of mass loss, so here I've written that they have 10 to the minus 6 to 10 to the minus 3 solar masses per year. This can be compared to mass loss rates of 10 to the minus 14 for our sun, just to give a bit of a comparison. They have a lot of material being thrown out. In fact, they lose over half of their total stellar mass over their lifetimes before even reaching the supernova stage. And so this is really a stage that is responsible for significant levels of both mechanical and chemical enrichment to the rest of the galaxy. And this is a phase that is not fully understood by the astrophysics community, and there are a lot of open questions still to understand. So just a bit more about stuff that I've been doing here at Chalmers is that I've been trying to study some red supergiants and yellow hypergiants. So although I showed you already that kind of crowded cluster where we see these different asymmetries and this sculpting by the presence of all these other massive stars, even for stars that aren't as in crowded areas like VYCMA and NML-SIG, as I've listed here, we still see asymmetry around these stars. And we actually think there might be underlying asymmetries in the outflows of the stars themselves. So rather than just being a nice spherically symmetric stellar wind being pushed out from the total surface of the star, we're starting to see evidence that there might be collimated or directional outflows from the stellar surface. And so there's a more complex series of processes going on where this material is being pushed out from the star. And we can relate this back to the chemistry that we're seeing around the star, because different species may be present in different areas of these outflows. So we can then relate this to what's happening in the stellar interior as well. And just as a final overview, so some of the work I've been doing has been looking at one of these red supergiants in our galaxy, NML-SIG. So this is present in the Cygnus region. It's about 5,000 light years away, and it has an age of about 8 million years. So we would expect, when looking at line profiles, and I've just put a quick example of some of the line profiles we see from it, we would expect to see a nice Gaussian, as I said earlier, where you've got it's broadened due to Doppler effects in the wind, or double horns, where you might have a disk around the star causing what's known as a double horn line profile. But actually, we're able to fit multiple Gaussians within quite broad line profiles when we look at different molecules that we've detected around these stars. And so this is really evidence that we're seeing multiple components, and therefore not just a nice spherical outflow from our stars, but actually multiple outflows. And so this shows that there's a very complex situation going on around these late type evolved stars that really does need more study. And there's a lot of open questions still to understand. So thank you all very, very much for listening, and I'll open it all up for questions.